You might say, why do we need to sublattice model? Let's go back to the idea of a model that is not just another example of, say we have a model that can fit the data sometimes but isn't physically correct. I mean, I showed in a binary system like NaCl, KCl, you have what you're really having is the chlorine is on one sublattice, so the sodium and potassium are mixing on the other sublattice, and it's equivalent to a one sublattice model. Supposing we had a model we know is not realistic, but let's say that NaCl and KCl were actually molecules. Okay, so what you would get is you would get NaCl molecules and you would get KCl molecules, and they're mixing on a sublattice. Okay. That would give you exactly the same equation in the binary system. X sodium chloride, G naught sodium chloride plus X ACl plus RTX1. You get exactly the same equation. Okay, so the binary system could be fitted just as well if you assume that NaCl and KCl were mixing like molecules on a sublattice as if you had the sodium and potassium in one sublattice and the chlorine on the other. So you could fit your binary systems up that way. But what would that give you along the stable diagonal here? This would simply be, if this was a stable diagonal, you'd have mainly sodium fluoride and potassium chloride molecules, which would mix ideally. There'd be no positive deviation along here. You just get sodium fluoride and KCl mixing, more or less ideally, which means the liquidus would be like way, way lower, hundreds of degrees lower. It just wouldn't work. So you might fit your binaries nicely, assuming a molecular model, which would be very simple, but it's not going to work in the reciprocal system because you have two sublattices, and if you don't take the two sublattices into account, then the whole thing completely screws up by huge amounts. The other thing that's different, this actually was taken as some of the initial evidence for molten salts. You remember that as you, if you take a system, we did this back a few weeks ago, we take a system AB, say a eutectic system, the limiting slope of the liquid is here if you have no solid solubility. Since in the limit you're coming in the very limiting case here, it's the excess terms become very small, it's only the ideal terms that Reynolds law applies. So remember, if we use this, the limiting slope here just simply gives the limiting slope of the liquid as you can use to calculate the heat of fusion. It depends only on the ideal terms. You all remember what I'm talking about? Okay, so this, if you take, say, sodium chloride, KCl, you're going to get a limiting slope here, which is given by, as you'd expect, the limiting slope, it's RT log. But supposing you take NaCl, KF, well, let's do it. NAF, let's go along here, NAF, KCl. Now, as I move along this line, I'm taking NAF, and I'm replacing it by KCl. But now, I'm replacing the sodium by the potassium, I'm replacing the fluorine by the chlorine. Okay, so ideal term, you have two ideal terms. You have this ideal term and you have this ideal term. Okay, so you're actually, as you're going from sodium fluoride to KCl, you're not forming one ideal solution, you're forming two ideal solutions. The sodium, you're getting twice the entropy. Potassium and sodium are mixing and the chlorine and fluorine are mixing. The result is, as you start off along this line, your liquidus line decreases at twice the rate. You have twice the limiting slope. Okay, because you're getting twice as much entropy. If this were a molecule, you wouldn't. If this was NAF, KF, KCl molecules, you would get the slope up here, but since you're getting double the entropy, you're getting double the, okay, you're getting twice as much entropy as you would. Okay, but then, so you start off dropping faster, but then you get the positive deviation because of this other effect. So initially, as you start off here, it goes down faster than it would if it was an ideal solution of just molecules, but then you start getting a positive deviation because of the other effect that I mentioned. And this was actually given as the first evidence back in the late 1940s that molten salts were in fact ionic liquids with two sublattices, was the limiting slope. This is a very easy thing to measure. And whenever you take one salt and you add another salt with a common anion, like NaFKF or NaFNaCl, you get a slope up here, all the same. Remember, it doesn't depend. Remember, we talked about it doesn't matter what the solute is. As long as you have no solid solubility, your limiting slope's the same. As long as you also, though, have the same number of new particles coming in. So if you take NaF and you replace it by KF, LiF, whatever, or NaCl, NaBr, as long as there's an ion in common, you'll always get this slope. If you replace it by a salt which has two different ions, you get twice the slope. And that was taken as the first evidence of the sublattice model for molten salts back then. Okay. All right, so here's the model, this nice model then. Let's say we have the G-naughts. These 4 G-naughts are quite well known from the literature. We've optimized our 4 binary systems for this particular system, so we have these alpha functions. We use this nice equation here, and we calculate the liquid surface over here. This is the experimental data, and we do not get this. This is not using the equation I gave you so far. What you get is, if you just do what I showed you, you get positive deviations, but you get too big. Quite a bit too big. It's much too flat. I think you actually get a small miscibility gap here. And this is always the case. If you use the equations that I just showed you, you get too big positive deviations. That I gave you another example. I think it was lithium fluoride KBr, in which you actually had a miscibility gap. If you use the equations I showed you, you get the gap, but it's way too big. It's too wide. It's too high. You overestimate the positive deviations. Okay, so if you use molecules, the bad model with molecules, you don't get any positive deviations, so that's no good. But if you take into account the 2 sublattices, you get the positive deviations for the reasons I stated, but quantitatively they're too big. Why would you say that was? What are we ignoring here? We're assuming ideal mixing. You don't have ideal mixing because these first nearest neighbor changes are quite strong. We're assuming, okay, the KCl, it was said, potassium likes to be next to chlorine, sodium likes to be next to fluorine. We're assuming that in the middle the number of potassium-chlorine bonds is Y potassium, Y chlorine. Actually, the system will have short-range order in order to stop that. In other words, there will be clustering. The potassiums will tend to cluster next to the chlorines, forming fewer potassium, fluorine, and sodium chlorine bonds, as few as possible. Okay, so you're going to get deviation, you're going to get short-range order. In the model I showed you, you're assuming you're forcing the system to have to be randomly mixed. And the system doesn't have to be randomly mixed. If potassium likes to stay next to chlorine, it will stay next to chlorine, and you'll have clustering. Now, it will still mix because of the entropy term, but they won't mix. It'll be a balance. It'll minimize its Gibbs energy. System will always, so if you put an unnecessary restriction on the system, or an incorrect restriction, in this case a restriction of forcing it to be an ideal mixture, this will always give you too big a Gibbs energy. The system, every time you give it you remove a constraint, the system gives it another chance to lower its Gibbs energy. It's always trying to lower its Gibbs energy. Okay, so that's why the unnecessary constraint of ideal mixing gives you too big a miscibility gap, too big positive deviations. If you allow the liquid to have short-range order, then it lowers its Gibbs energy, so you get lower positive deviations, smaller miscibility gap. Okay, and these first nearest neighbor interactions are strong, even in a system like this, so the short-range order basically can't be ignored. Okay. We're coming to the quasi-chemical model again. If the delta G exchange is quite small, then you can ignore the short range order, but it's got to be really small. Well, just to go back to your question there about the radius of the ions, you see that here you have relatively small positive deviations because sodium and potassium are the first 2 alkalis, and fluorine and chlorine are the first 2 halogens. But I showed you another example, lithium fluoride, potassium bromide. There's a bigger difference between fluorine and bromine, between lithium and potassium, so the radiuses are different. Radii are different, so you get a bigger delta G exchange. The bigger the difference in the radii, if you went lithium, cesium, fluorine, iodine, you're going to get a huge miscibility gap because of the difference in the radii. So this is going to be the lowest probably. Okay, so it's the short range ordering of first nearest neighbors that are the problem. Okay, so we have our exchange reaction. So we have our exchange reaction in which we have NaCl nearest neighbors plus Kf nearest neighbors form NaF nearest neighbors plus KCl nearest neighbors, and these are preferred. Okay, so there are going to be more of these than there are in a random mixture, and fewer of these than there are in a random mixture. Okay, so let's go back. I'm kind of doing this historically, but the reason they do it, slide 22. So we're going to have to go to slide 22. Sorry, maybe next year I'll kind of put some of these things in a little bit better order. Anyway, it's kind of an historical thing in the course here too. Okay, let's say you have Vx plus Ay forms Ax plus By. A and B are the cations, X and Y are the negative ions. There's your delta G exchange. The probability of an Ax pair is, sorry, I'm using the old notation. This should be little ya, yx. Now these are the site fractions. The previous notation, this was ya, this was yx. So this is, in an ideal solution, the probability of an Ax pair is simply xaxx. Now it's xaxx plus little y. Not to be confused, this y is another. This has nothing to do with the site fraction. This is a variable which we're going to optimize. This indicates the deviation from randomness. Okay, so we're assuming then that if the delta G exchange is negative, in other words, if these are the stable pair, then y will be positive. The number of Ax pairs will be greater than the ideal value by y. The same thing with the By pairs will be greater by y, and the number of Bx and Ax pairs will be less than y. Total number of pairs, of course, stays constant. Okay, so y is a variational parameter. Okay, the more negative is delta G exchange, the greater will be y. Delta G exchange is positive, y will be negative. If delta G exchange is 0, y will be 0. So that indicates your short range order. Okay, so now we rewrite the equation. Remember, in the previous equation, the G naught Ax was multiplied by xaxx, which is the probability of an Ax nearest neighbor pair. Now we multiply it by the probability of a nearest neighbor pair, which has been increased by y. And the same thing for all the pairs, and the number of Ays would be G naught Ay. Previously it was xaxy, now it's G naught Ay. Minus the configurational entropy plus Gxs. The configurational entropy, okay, we still write it as xa log xa plus xb log xb, same thing. It doesn't mean it's a random mixture now. This is just your A's and B's are mixing. On each sublattice, the A's and B's are mixing randomly on the sublattice, but the number of pairs is not necessarily the same anymore. And similarly now you had the, oh sorry, no, okay. I'm wrong. This is this is like the quasi-chemical model. In the quasi-chemical model, on the single sublattice, we mix the AB, AA, and BB pairs over pair sites. Now we're doing the same thing. We're mixing the AX pairs, the BX pairs, the BX pairs, the AY pairs are being mixed over pair sites. Okay, so we have the number of AX pairs, log times the number of AX pairs, plus the number of AY pairs, log number of a fraction of AY pairs, divided by the number of pairs in the ideal solution, and then we add on the ideal term, exactly as we did in the quasi-chemical model for one sublattice. Remember, in the quasi-chemical model for one sublattice, the configurational entropy was minus RZ over 2 times the number of AA pairs times the log of the AA pairs, plus, first of all, we mix the pairs, XBB plus XAB log XAB. We mix the pairs over the pair sites. Then we said that overcounts the pairs, because if this is a BB, this can't be an AB, so you divide by the number of pairs in the ideal solution. And then you add on the ideal term. Okay, so in the one-dimensional quasi-chemical model, you mix the pairs over pair sites, XA log XAA, XBB log XBB, divide by the number in the ideal solution, and then put on the solution. the ideal solution term. So that in an ideal solution, this whole first term is 0. Okay, now we're doing the same thing, but we're talking about second nearest neighbor, or first nearest neighbor pair sites in a 2 sublattice model. Okay, so now we have these are your pair sites. And we're talking about the number of AX pairs, the number of BY pairs, AY and BX pairs, and so on. So this is the number of AX pairs times log the number of AX pairs, number of AY pairs, log the number of AY pairs for all 4 kinds of pairs. That again overcounts the pairs. If this is AX, obviously that can't be BX. Okay, so you divide by the number of pairs in an ideal solution. In an ideal solution, it's XAXX is the ideal number of AX pairs. When the delta GX changes 0, or like here, when the delta GX change, when the omega term is 0, here when the delta GX change term is 0, this is the number of AX pairs in the ideal solution, and so on. And then we add on the ideal term. So if the delta GX changes 0, then you have an ideal solution. This entire term here goes to 0, and the first term is back to your old ideal mixing term. Okay, so that's your quasi-chemical model extended to the 2 sublattices. Okay, if y is equal to 0, then this is simply the equation that I gave you before. Okay, but now y is not 0. How do we find the value of y? Well, we simply set dg dy equals 0. I'm forgetting the excess Gibbs energy terms here, which are the alpha terms, because I'm trying to show you the most important terms. The alpha terms I showed you before are the second nearest neighbor terms. They're secondary. This is the most important term here. Okay, so in this term, okay, if you take dg dy equals 0 at constant composition, so your XA, XX, XB, XY are constant, your overall composition of the system is constant, all you're doing is trying to find the short range order parameter that gives you the minimum Gibbs energy, which is what the system will do. So if you set dg dy equals 0, and you can try to play that with yourself, it's not very difficult, you end up with, again, an equilibrium constant. And this is the equilibrium constant for the exchange reaction. Okay, this is the number of, this is the equilibrium constant for this reaction. This is the mole fraction of AX pairs, the mole fraction of BY pairs divided by the mole fraction equals E times the, okay, so this is your, Z, by the way, is the first nearest neighbor coordination number. Okay, because for 1 mole of solution, you have Z moles of nearest neighbor. Okay, so you get your quasi-chemical equilibrium constant just as before. These are the number of pairs on each site, the number of AX pairs, the number of BY first nearest neighbor pairs, and the, okay, when delta GX changes 0, then the Y comes out to be 0. If delta GX change becomes more and more negative, Y becomes more and more positive. Okay, so it's this quasi-chemical model and the 2 sublattice model, and you're talking about first nearest neighbor pair sites now. And this is Z because if there's you have 1 mole of positive ions, 1 mole of negative ions, so you have Z as your first nearest neighbor coordination number. It's the number of positive ions around a negative ion, or the number of negative ions around a positive ion. Now, I've kept it simple by talking only about monovalent. It's only AX, it's not A2X for the moment. We just keep it simple. Now, then you can solve this equation then, and this is the way we do it in FactSage. This equation is then solved numerically. Quasi-chemical equation is solved numerically in order to get you the value of y. You put that back into these equations here, and then you end up with the thing. And then you will find that this lowers the, this decreases the amount of positive deviations that you get. Okay, now, that's the way we do it now, but back in the 1960s and 70s, but also for that, then you have to have the software for this and everything. There's an approximate way of doing this. If y is small, and this is the way that it's done by SGTE and thermocalc and so on for them. Let's suppose that y is small. So we're going to try to approximate. So in principle now, you no longer have a simple polynomial. You've got to solve this equation numerically to get the value of y, put it back in, and you end up with a complex thing. The way of, if y is reasonably small, not too big, so you have a fairly small short range order, we are taking the logarithm of each side now. So first of all, I'm taking the logarithm of this side. So this is nothing. This is just taking the logarithm of this side equals the logarithm of that side. But now we're going to do a first term Taylor expansion. Log of 1 plus y over x is approximately y over x if y is small. This is your first term in your Taylor expansion. So if we expand these as a Taylor expansion, take only the first terms, then we can make the whole thing linear. We replace this logarithmic term by y. We end up with, then if you can do the solution yourself, you'll end up with y is approximately equal to the product of the 4 site fractions. And similarly, you can work out the configurational entropy as given by this. Substitute the whole bloody thing back, and what you get is you get the terms that we had before in the old equation, xaxx plus xy plus y plus the gxs term. So this first part is the old equation that we showed you on the other slide, and you have one additional term here which takes account of the short range order approximately. But this then permits you to maintain the whole thing in the polynomial formalism. So this equation here is the same one I showed you before, and then you have this additional term here. The greater is delta gx change, the bigger is this term. And this is your approximation for your short range order. And it's always negative. This is delta gx change squared, doesn't matter what the sign of this. It's always negative because the short range order will always decrease your Gibbs energy because it gives the system one less constraint to worry about. Okay. So we add on this term. Okay, so you might want to do this mathematics yourself. It doesn't really matter. This was then on slide 22. Play with the math, but it's right. And this, after all that, it ends up to be a very simple polynomial term here, the product of all 4. So this term also, by the way, it's the product of all 4 site fractions. So that's going to have its greatest value in the center of that composition square. And it's always negative. Okay? So that takes us back to this. So that term is negative, so it brings down the miscibility gap. If we didn't include that term, the miscibility gap was too big. Now it brings it down, and it brings it down most in the very center, which is what you want to do. Right. And of course that term is that's a purely reciprocal term. It's the product of all 4 site fractions, so it's 0 all around the edges. It has no effect on the binaries. It's only a reciprocal term. One of those y's has got to be 0. And when you use that extra term, then this is what you get. This is the experimental diagram, and this is the calculated diagram with no additional ternary terms. We have the G-naughts of the pure materials, which you get from the thermodynamic compilations. We have the alphas, which are the binary fits, second nearest neighbor, and then we predict the phase diagram just using the thing. It's not too half bad, eh? This is 642 and a minimum point here. This is 648. So this gives you some belief that the whole thing is correct. Actually, I had the opportunity to work with Milton Blander, who died a couple of years ago, but Milton Blander was one of the pioneers in the 60s of the sublattice model. And he first did this calculation. Damn thing didn't work. Then he got the idea of this short range order term. In those days they didn't have the computers and that to solve the whole thing, so he developed this Taylor expansion thing. And he calculated this diagram all out by hand. And he says that was one of the greatest hallelujah moments of his life when he just, God, the damn thing works. So anyway, so there is the model. Now if we go to the, I believe that was here. Okay, this was the equation, and that's why we then add on this term here. Okay, this was going back to the number, whatever, 29A, I believe it was. So this is the big lambda term, also called the Blander lambda term. It's the product of the 4 negative product of the 4 site fractions times a constant, lambda, where the constant lambda is given by delta gx change squared over ZRT. Now, if you want to approximate, this is what you do here. You can get lambda this way. Or you can treat lambda if you want an adjustable parameter. If you want an adjustable ternary parameter, you first of all take this value, you take lambda to be equal to this. If that doesn't work, then you want a ternary term. Your simplest ternary term would be to make lambda adjustable. That'll bring the whole thing up and down and make it biggest in the middle. You can add other ternary terms later. Okay, but often then lambda is treated as a ternary term. But if you want an approximation for lambda, it's del of g exchange squared over ZRT. And lambda should always be positive, because this whole term should be negative. Okay, so lambda is approximated by del of g exchange squared over ZRT. And if you want to then do further adjustments, your first step would be to play with lambda a little bit and introduce it as an adjustable ternary parameter. I've written the alpha functions as polynomials in each binary system. So in the sodium fluoride, potassium fluoride system, the alpha function is the Redlich-Gister parameters times y sodium minus y potassium to the I system. Normal. These are your binary parameters of the Redlich-Gister expansion for the alphas in each of the binary systems. Okay, so this is then this basically is the model that's used by most of the people in CalFed if you have a two sublattice model with, well, expanded. I think you can have more than two sublattices. We'll get to that in a minute. But it's always, they always do it with they don't really use quasi-chemical. The only short-range ordering is taking this term into account. Some people understand that term should be there. Most people don't put that term in because they don't understand what it's all about, so they always get two big deviations. The people at Thermocalc, Matt Zillert, put that term in, but they generally treat it as a lambda term. They never give Blender credit for it, but Blender taught them what to do. So the short-range ordering is taken into account by this type of term here, and it's not trivial. Okay, so this is basically your two sublattice model in the compound energy formalism when you have the same number of sites on each sublattice. That's how it works. You can add some other ternary terms as well. Okay, any questions so far? Okay, let's continue now with some solids. So that we're going to continue with the polynomial model. So this is the polynomial model with the short-range order. If you take into account the short-range order, you use the big lambda term, which is what they do. Let's go to slide number 23. Okay, this has become called the compound energy formalism. I'll explain why we call it the compound energy formalism later, but basically the compound energy formalism is the polynomial sublattice model. It's the polynomial sublattice model where you don't really take into account short-range order, but you can take it into account approximately through this big lambda term. But basically, it's the equations I just showed you. You have an ideal mixing on each sublattice. Well, you have ideal mixing on each sublattice. And the big lambda term is just basically you can make a correction if you want. And also in the compound energy formalism, as it's talked about, and when you hear, I mean, there's a little confusion in terminology, but when CalFed people talk about compound energy formalism, they're also talking about fixed number of sites on each lattice. A ratio, like you have, in sodium chloride, you have same number of sites on each sublattice. Magnesium chloride, you have twice as many sites on the anion sites as the cation site. This is appropriate for solids. In liquids, of course, it can vary. Okay, you can go sodium chloride and magnesium chloride are completely miscible. So the ratio of lattice sites is changed. But for solids, it's always got to be constant, of course, because you've got a rigid lattice. Okay, here's your compound energy formalism, known as the CEF, which again goes back to the molten salt work of Blender and those people, although they should get more credit. People talk about the compound energy formalism of Hillard or whatever. Hillard has made many additions to it, but it's not really his basic idea. Example for two sublattices. Always a fixed number of sites per lattice. So these are solid, or solids, or well, the liquids as long as you have a fixed number of sites. Liquids as long as they're always the same valence. So the examples I just showed you work because they're all univalent ions. But if you mix sodium chloride and magnesium chloride, then you can't do it. Okay, we write it this way, ABXY, or AB brackets XY brackets. You have A and B are on one sublattice, X and Y are on the other sublattice. Let's, for example, assume that on lattice 1 you have 2 moles of sites, and on lattice 2 you have 3 moles of sites. So your corners now are A2X3, A2Y3, B2X3, and B2Y3. Same number of sites, 3 to 2. Okay, so it doesn't change as you move around in the composition. Okay. The Gibbs energy per mole, this is per mole, this is a mole, is written as the same as before. YA, YX, this is the probability. These YA and YX are the site fractions. YA is the number of A's divided by the number of A's plus the number of B's, and so on. The A's and B's are mixing randomly on one sublattice, the X and Y's on the other. So it's the probability of an AX pair is YA, YX times the Gibbs energy of pure A2X3 and so on, same as before. Plus now you have 2 moles of A's and B's are mixing on 2 moles of lattice 1 site, so you have a 2 over here, 2 RT, YA log YA plus YB log YB. And you have X's and Y's mixing on the other lattice, so you have 3 moles RT, YX, YX. Plus, and then these are the alpha terms as before. Now we have, I call it L, but this was alpha. It's just a polynomial. YA minus YB to the I. This is the ABX. So this is it's written AB slash X. So these are the binary terms and this binary over here. And these are due to the AB interactions, second nearest neighbor AB interactions on the AB lattice when the other lattice is completely occupied by X. So the negative ion, or the lattice 2, is completely occupied by X, and these are the second nearest neighbor AB interactions. So this is your binary terms. This is fitting the binary along here. Same for all 4 binaries. And this got lost. Oh, sorry. And then I didn't put in the big lambda term. 1, 2. Sorry, here it is. This is your big lambda term. L, A, B, X, Y. This is the terminology. This is what I called before big lambda. This is minus big lambda. Okay? Before it was minus big lambda. So this is your probability of YA, YB, YX, Y. This is then this, what they call the ternary term, L, A, B slash X, Y. This is pretty much the terminology they use, although they'll write AB slash X or sometimes AB colon X. Depends on whose paper you're reading, but these Redlich-Kister terms are written as I, L, so this is A, B slash X, so this is your Redlich-Kister term for the AX, BX binary side. So it's the AB second nearest interactions when the other lattice is occupied by X, or sometimes there'll be a colon here, or sometimes there'll be a semicolon or something like that. This then is a reciprocal term, which is 0 in all 4 binary edges, and this will be written as L AB slash XY, or maybe AB colon XY or something like that. And L should be negative because it's basically a short range order correction. And your first approximation for L should be delta GX chain squared over ZRT, but you can treat it as a adjustable parameter. So this would be the compound energy formalism, more or less using the notation of Calfat, using the small y's for site fractions, and using the Redlich-Kister terms here to indicate that this here is the Redlich-Kister term for the XY interactions when the other sublattice is occupied by A, so these are binary terms. So these are your site fractions. Later on I'll talk about big YI, which are equivalent fractions, not to be confused. G0 A2X3 is the molar Gibbs energy of 1 mole of A2X3. I haven't talked about equivalence yet, but it's 1 mole of A2X3. A2X3, A2Y3, and so on are the end members. So these are your 4 corners here are your N members. and we need the Gibbs energies of the end members. There is one end member for each lattice pair. Okay. So you have YA, YX times the Gibbs energy of the AX end member, and so on. If you wanted to extend this to more end members, so if you wanted to have ABC, XY, ZW, right, then you would simply have a term for every end member pair. Okay, so term for every end member pair, so your Gibbs energy would be YA, YX times G naught of your AX end member plus YA, YY times your G naught of your AY end member, and 1 for every pair. So you'd have 1, 2, 3, 4 times 3, you'd have 12 end members. Okay, and then on the entropy side here, you'd have terms for YA, YB, YC. Here you'd have YX, YY, YZ, YW. And you would have a term for every binary. Okay, you just add them up. And you're going to have a reciprocal, you're going to have a delta G exchange term as well for every possible exchange reaction. AX plus BY gives you AY plus BX, AZ plus BW gives you AW plus BY. Every pair will have every possible exchange reaction between pairs will have. And that's the compound energy formalism. I took 2, 3, obviously, whichever, but it's, so 2, this here is a number of, this is A, N, B, M, this would be N, obviously, M, you figure all that. Okay, so the extension to 3 or more sublattices is evident. This would apply to a liquid solution as long as all the salts had exactly the same stoichiometry, 3 to 2. Okay. Or it'll apply to a solid phase. But generally we're using this for solid solutions. Alright, I'm taking this now from I'm going to do this a little bit quickly here because I'm going to come back to it a bit later. But we're treating, this is a paper from myself and Yunbei Kang a few years ago, the magnesium Itrium system. I'm sure you've been doing this kind of stuff already. Here we have a non-stoichiometric compound, a Lave C14 structure phase, and based on Mg2Y, so it's basically around 33%, but we see that there is a non-stoichiometry for this phase. Okay, so basically there's 2 sublattices. There's a magnesium sublattice and an Itrium sublattice, and there's twice as many sites on the magnesium sublattice as on the Itrium sublattice. But in this particular system, you can get non-stoichiometry, indicating that in this particular case you can have some substitutional disorder. That is, some magnesium can actually go on to the sites normally occupied by Itrium, and vice versa. So we actually would write the thing out this way. We would write magnesium, Itrium 2, magnesium, Itrium 1. This is mainly occupied by magnesium. This is mainly occupied by Itrium, but you can get some Itriums over here and you can get some magnesiums over here. Okay? And that's why you get the non-stoichiometry. It's clearly more over to this side, 33% is around here, so clearly you're getting more. Which side is magnesium? This is magnesium. You're clearly getting more magnesium on the Itrium. You're getting excess magnesium, so you're getting more magnesium on this side than you're getting Itriums over here. Or else this would then be open that way. You do remember some time ago we did a Gibbs energy for a system like this, magnesium Itrium, or when you have a compound, you're getting a Gibbs energy curve that comes down very, very sharp. As the Gibbs energy curve comes down very, very sharply, this becomes more and more negative. So, how do we treat this now with the, we can treat this using the compound energy formalism. And we treat this using the compound energy formalism as follows. We actually treat it as a reciprocal system. And here we have Mg2y. Here we have Y2 Mg. Let's go back to magnesium, Itrium. So here we have Mg2y. This is your main, it's mainly over here. This would be Y2Mg. This would be Mg2Mg. and this would be Y2Y. So you have 4 N members. Your main M member is Mg2Y. Then you would have an M member, Mg2Mg. Mg2Mg means that all the yttrium sites are now occupied. All the sites on this lattice, which are normally occupied by yttrium, are now occupied by magnesium. Okay, so this is your hypothetical N member. You'd never get to there. Okay, this is, or you can think this magnesium is what we call a substitutional defect. So you have mainly Mg, or your main, I mean this whole system is down here. Okay, but as you're moving along this way, you're replacing some of the yttrium by magnesium over here. This is now going all the way to replacing the whole thing. And as you go along this way, you're replacing some of the magnesium here by yttrium. So you're replacing some of the magnesium by yttrium in this area. And as you go along here, you simply, hypothetically, you go all the way where all the magnesium, sorry, Y2. No, what am I doing? This is back at. This is Y2. Y. Mg2Y, Y2Y, Mg2Mg, sorry, I'm backwards. Y2, Mg, is that right? That's got to be right. Yeah. Okay. So I'm starting here with M. This is all my real solution is here. If I move along this range here, I'm replacing some of the yttriums by magnesium as a substitutional disorder. And this is just hypothetically, if you go all the way, you're Mg2Mg. Here I'm replacing some of the magnesium by yttrium on this sublattice. If you went all the way, you'd end up with this hypothetical N member. And over here, I've replaced everything on this sublattice and everything on this sublattice, so this is really something very hypothetical over here. But that's my hypothetical. So I'm in this reciprocal solution with 2 sublattices, okay, but my actual main composition is only over in this region. The rest of the thing is kind of hypothetical. Okay. So, how do we treat the Gibbs energy then? We treat the Gibbs energy as, okay, the sublattices are called little a and little b to separate them. They're no longer cation and anion sublattices, they're A and B sublattices. Okay, so the Y's are the site fractions. Y magnesium A is the site fraction of magnesium on the A sublattice. This we'll call the A sublattice, and this we'll call the B sublattice. So it's the site fraction of magnesium on the A sublattice times the site fraction of magnesium on the B sublattice times the Gibbs energy of this hypothetical compound. Okay, here I'm using the big G because that's what, not the molar, because that's how people do it. Also this G, Mg colon Mg is again the symbolism you use, but G, Mg colon Mg, and my notation would be G of Mg2 Mg. We don't put the 2 in, it just means all of this. This is the N member up here, in which you take this, the 2-to-1 stoichiometry is taken into account. So G, Mg, Mg is really the Gibbs energy of Mg2 Mg. So this is exactly the equation we used before. This is the sublattice equation. Ymg on the A site, this is one N member. The product of the site fractions for this N member, product of the site fractions for this N member, and so on, plus the ideal mixing term, a 2 here because you got a 2 moles here, times the mixing of the magnesium and yttrium on this site, plus the mixing of magnesium and yttrium on this site, plus now you can put in, if you want, you can have binary terms here. These terms will be small. These are the main terms here. These will really be small because you're really only dealing with a small area, but these are your binary terms. These are really your second nearest neighbor terms. So this is your interaction of, what is it? Magnesium with yttrium, the second nearest neighbor. So this is magnesium reacting with yttrium on the same site when this site is occupied by yttrium, for example. Okay, so this is magnesium with magnesium when the other site's occupied by this. So there's a binary term for each. This I forgot about. I've only used this and this. But these will be, generally these binary terms will be almost 0 if you're dealing with these things. But these are your second nearest neighbor terms. Your main terms, as always, are these G0 terms up here. Okay. Now, what value should we have for this G0? This here, this is the MGY. So this is your main, this is your Gibbs energy down here. And this is your main Gibbs energy of forming this compound. This, you might say, well, this is the Gibbs energy of magnesium. But no, it's not the Gibbs energy of magnesium. This is the Lavase phase. It's a Lavase structure. This is the Gibbs energy of the Lavase phase when all the yttrium have been replaced by magnesium. This is not hexagonal compact magnesium. This is a hypothetical thingamajigger where you've taken the Lavase Mg2y and you've replaced all the yttrium by magnesium on the other lattice site. So this is going to have a very positive Gibbs energy. This is an unstable affair, right? This is going to be equal to the Gibbs energy of hexagonal compact magnesium plus something. And this thing over here, Y2Y, this is not the Gibbs energy of real yttrium. This is the Gibbs energy of a hypothetical structure in which you've taken the Lavase Mg2y and have replaced all the magnesium by yttrium. These are called, this is magnesium here is called a substitutional defect. In other words, you're mainly Mg2y and the magnesium over here is a substitutional defect. It's magnesium, a point defect, magnesium occupying a site where you normally find an yttrium. And this yttrium here is a point defect, okay, occupying a site where you normally find the magnesium. Okay, so this is basically the energy of introducing a point defect. Or if you wanted to say it here, the Gibbs energy of Mg2Mg minus the Gibbs energy of Mg2y is basically the Gibbs energy of putting the molar Gibbs energy of replacing the yttrium by the magnesium. Okay, so that it's a parameter of the model. It's not Gibbs energy of real magnesium, it's a parameter of the model. This over here is also a parameter of the model. This minus this is the energy per mole putting this point defect. And this thing is basically the sum of them. This is replacing, this is even more so. This is a Y2Mg, this is the Gibbs energy of this thing, is the Gibbs energy of the Lavase phase replacing all the magnesium by yttrium and all the yttrium by magnesium. So this is basically the sum of this plus this. You're replacing everything. So this difference here plus the equivalent difference here should give you that difference there, basically. Or, if you want to look at it the other way, this is what I was showing you here, where let's take the Gibbs energy again, and this is your Mg2y. And this is the 1/3, 1/3 here. And this here is your magnesium, and this is your yttrium. Okay, the Gibbs energy of a compound comes down very, very sharply. Okay, the more narrow this, as we talked about a month ago, the narrower this is, the narrower the stoichiometry range of the phase diagram. Okay, so this point here is your G. I wish these things would work. This point up here, your compound is really, this is the area we're dealing with. On the phase diagram, remember, it was only over a very narrow region. This is the only region here that has any real physical significance. The sharper that is, the narrower the single phase region is. This point up here, this is your G naught of Y2Y. This point here is your G naught of Mg2Mg. Your real Gibbs energy of real yttrium might be here. This could be the Gibbs energy of real yttrium is down here. This is the Gibbs energy. This distance then is this energy to form the defect. This distance is energy to form the defect. The further you put these up, the narrower your single phase region is going to be. So this G naught magnesium is going to be very positive, or at least this difference here. The more positive you make this difference, the greater is the steeper this thing goes up, the narrower is this region, the narrower will become your two-phase region on the left side. The more you put this thing up higher, or more positive, this goes up steeper, the narrow is your two-phase region on the right-hand side. So those are your main parameters that are affecting the thing. Okay. By the way, this point here, you might think that this point was G naught of Mg2y, but it's not quite. G naught of Mg2y is the Gibbs energy of hypothetical Mg2y when all these sites are occupied by magnesium and all these sites are occupied by yttrium. But in real Mg2y, even at the Mg2y composition, there will be some yttrium over here, and there'll be some magnesium here a little bit. Okay, so this will actually be a little bit higher. Okay, so the actual minimum of the curve is not exactly the Gibbs energy of the real compound. The minimum of the curve is the Gibbs, sorry. No, the minimum of the curve is the Gibbs energy. Back aspirin. This is the actual minimum, this is the experimental minimum of the curve. But this is not G naught Mg2y. G naught Mg, actual G naught Mg2y, your end member Gibbs energy is going to be a bit lower. Your end member is not real. Your end member is not real Mg2y. It's a hypothetical Mg2y with no substitutional disorder. Real Mg2y will have some substitutional disorder, so it'll be a little bit higher. Okay, so if you were to look in the literature and you were to find a Gibbs energy, somebody's measured the Gibbs energy of Mg2y, he's measured the Gibbs energy of real Mg2y. This is not exactly the value you should use for your end member Gibbs energy, because your end member Gibbs energy is a hypothetical thing that's a bit lower. Okay, so these are your model parameters. Your Mg2y's will be pretty close to the Gibbs energy of the real material. These are hypothetical parameters. The higher you put these G naught, GM, GMG, and GYYY, the narrower is your two-phase region. This thing up here, it should really just be the sum of this and this, so it's not an independent thing. And now you can play, these are your main parameters that you play with here. This G naught MGY, this basically is the stability of that compound, and these two terms here, okay, tell you how wide it's going to be, how wide the mean stoichiometry is going to be. Okay, and then these final binary parameters here, if you want to do some fine tuning, you can fiddle around with those things as well, but usually they don't make an awful lot of difference. This is your main stuff up here. Okay, these are going to be really secondary. And you can look down further in here, or you can read the paper if you want, but you see this is the result we got. Obviously this side we put more magnesium over here, so this magnesium was not quite so high. Sorry, this was the, yeah, so this magnesium was not this side, however, this was much higher than this, because therefore it opens up on the left side, not so much on the right hand side. And the parameters are listed further on here, play with them and so on. Okay, but I'm trying to give you the general idea. Okay, so that shows you how you can use the compound energy. Now in this particular case, I would have to admit that that big lambda term really doesn't make an awful lot of difference. I mean, you can, and the binary terms don't either. These are your main. This term here, G naught Mg2y, is going to be your main term, which fixes the stoichiometry and which really fixes the general, just the melting point of the compound. The more that's negative, the higher the compound will melt. These two terms, the higher they are, the narrower is the two-phase region. The binary terms and the big lambda term are truly minuscule. Again, the big lambda term, remember, it's only important in the middle, and you're far from the middle. The binary terms also remain important in the middle of the binary systems. You're way over in this corner here. So there's only really two terms that matter. The two terms that matter are the three terms, the G naughts. These three G naughts, this G naught can just be this, basically the same. So that's how you would apply the compound energy formalism to a non-stoichiometric solid with substitutional disorder. So remember then that these G naughts in this equation are not real Gibbs energies of end members, they're parameters of the model. This is why it's called the compound energy formalism. See, it's based upon the reciprocal model, and the reciprocal model that we talked about for sodium chloride, potassium fluoride, these are actual compounds. Sodium fluoride, potassium chloride are real compounds. Here we're writing it out as if these were compounds. But these are not. This is a compound, but these are not compounds. It's a compound energy formalism. You're writing these as if these were real compounds, but they aren't. This GMGMG is the Gibbs energy of Lave's phase with all the yttrium substituted for magnesium. It's not a real compound, it's a hypothetical compound. Okay, it's a compound energy formalism. Okay, but the whole thing fits into the simple model. And we'll see that this whole thing was really quite brilliant as we go on. We'll find there's all sorts of systems which are not really compounds, but you can use the same formalism. I'll come to that a bit later. And okay, again, you can extend this to models with 3 sublattices, as I said, and then you have more n members. That's all. If you're dealing with a system that's really where the only real part is in this corner, only real compounds are down here, then clearly these are hypothetical things, and the binary and the reciprocal term are quite secondary. I'll show you more examples later of non-stoichiometric compounds where you have other kinds of disorder other than substitutional disorder, where you introduce interstitials and vacancies and so on. For all of these, though, you can still use the compound energy formalism, which is really quite brilliant. Okay, so that's your compound energy formalism as it's normally used. These are the equations you use where you have fixed ratio of sites on the 2 lattices, as is always has to be the case for a solid, and is sometimes the case for a liquid. Now the question is, what do you do if you have, now we're going back to liquid solutions like molten salts, ionic liquids again, and now I'm going to introduce the possibility of having variable ratio of the number of sites. So we're taking, say, liquid of sodium chloride and MgCl2. In an MgCl2 you have twice as many anions as cations. So you have twice as many anion sites as cation sites. Meanwhile, in NaCl it's 1 to 1. The 2 are completely miscible, so the ratio of the first nearest neighbor core, the ratio of the number of sites has to change as you move across the system. And so how do we take that into account? Okay, I will talk for 4 more minutes just. Okay, this was actually done too in the past, a few years ago by Blander and the boys. I'll just introduce it in a simple way. What's going to happen if we take sodium chloride as your solvent, and into sodium chloride we introduce a small amount of calcium chloride? And there's a big difference between what happens if you do it in a solid and if you do it in a liquid. Let's say we do it as a solid. There's your sodium chloride. Pluses are sodium, the negatives are chlorine. And now I'm going to take sodium chloride, I'm going to put in a small amount of CaCl2. Let's say 1 molecule of CaC, 1 calcium, 2 chlorines. What happens is the chlorine, I take 2 chlorines and 1 calcium, and they replace 2 sodium chlorides. So 2 NaCl's are replaced by 1 calcium and 2 chlorines. The 2 chlorines replace the 2 chlorines, but 1 calcium replaces 2 sodiums. The only way to do that in a solid is for the calcium to replace 2 sodiums and for there to be a vacancy. You remove 2 calcium, you remove 2 sodiums, replace it by a calcium. The chlorines stay the same. Okay, but now you've introduced 2 particles. You've introduced a calcium and a vacancy. So you've introduced twice the entropy. If this calcium and sodium can move apart, can go wandering off by themselves, they're randomly distributed. Okay, so over the cation sites you're distributing sodiums, calciums, and vacant cation sites. Now, if you add enough calcium, there will start to be pair formed. You'll have the tendency will be for the vacancy to go next to the calcium ion. Remember, the calcium ion here now is a doubly charged site. The vacancy has no charge on it, but it's surrounded by negative ions, so it effectively has an effective negative charge. There should be a positive charge here, there isn't. So it's as if there's a negative charge. The vacancy is going to tend to form pairs, so you do tend to get pairs between your calcium and your vacancies, but in dilute solutions this isn't the case. The vacancies and the calcium can go off by themselves. So every time you add a calcium, you're really adding a calcium and a vacancy, so you're adding double the entropy. Now if you take a liquid, however, there are no vacancies in a liquid. You can't, well, they used to think there were, but there's no evidence for vacancies in a liquid. And what happens when you add calcium chloride to sodium chloride is the calcium replaces the sodium, the chlorines replace the chlorines, no vacancies are formed, and simply locally around the calcium the coordination number changes a bit. The liquid is labile, it can accommodate. You're not stuck with a rigid lattice, so around the calcium ions, locally the structure changes to accommodate that fact. You're going to get a few more chlorines around the calcium than you are around the sodium. But no vacancy is introduced. What's happening then is simply the sodium and the calcium ions mix randomly, but there's no vacancy, so you get less entropy. But the coordination number ratio now is changing as you move across. The more calcium you add, the ratio of the cation to anion sites, the number of sites on the sublattices change. Okay. So now we have to somehow take that into account. This model, by the way, in the liquid phase, saying that in a liquid phase, you don't form vacancies. In other words, the calciums replace the sodiums with no regard for the charge. The doubly charged and the singly charged or triply charged ions just mix on the sublattice. The number of sublattice sites change. That's called the Temkin model, because of the Russian who in 1948 proposed the Temkin model. Okay, the Temkin model is the model saying that you don't have vacancies in liquid. There's the cations mix on cation sites, the anions mix on anion sites, regardless of their charge. Okay, what is the simple best evidence for this? If we were to take, say, sodium chloride over here, phase diagram, and we add calcium chloride, we measure the liquidus, no solid solution, you get a limiting slope. Same thing I said, the limiting slope corresponds to simply 1 mole of calcium, a single entropy, calcium replacing the sodium, just like any other solution. If you had vacancies, then in the limit, each calcium would introduce a calcium and a vacancy, which would form 2 independent entities which mix, and you would get twice the limiting slope. But you don't, you get 1 times the limiting slope in all these systems. So that shows this, plus all sorts of other things show that it's correct. One final thing, and this is interesting, is if you take a number of systems, you look in the phase diagrams for Ceramus book, and you take systems, you generally need more than 2 charges. Let's say you take sodium fluoride, and over here I'm adding, say, lanthanum fluoride, but it also works for sodium. Take the temperature. I thought a long time that this was an error, because it's a subtle effect, and these phase diagrams are measured a long time ago, but you find many, many systems in which the phase diagram sort of looks like this. And then you have phase diagram continues on over here. But over here you have a solid solution of sodium fluoride and lanthanum fluoride with a maximum. And this solubility is usually only, 5% or 3% or something like that. So you have a very narrow solid solution range, 3–5%, but it goes through a maximum. And there are many, many systems are like that. It seems to be the rule rather than the exception. When this here has different charges than this. So remember, lanthanum fluoride now is the same thing. This is lanthanum 3+, fluorine-. So if in the solid solution, if you add lanthanum to sodium fluoride, you're putting in lanthanum and you're forming two cation vacancies. If you put lanthanum, however, into the liquid phase, the Temkin model applies and you're only forming the lanthanum. So what's happening is the solid solution is entropically stabilized, at least for a small region. As I'm adding to the liquid, I'm only adding 1 foreign entity, 1 foreign particle, lanthanum, which mixes. As I'm forming the solid solution, at least in dilute solution, I'm forming a lanthanum and 2 vacancies, so I'm getting 3 times the entropy. Okay, so the solid solution is stabilized because of this additional entropy, which gives you a maximum. It stabilizes, the solid solution is stabilized relative to the liquid, pushes it up. It's not enthalpy, it's entropy, it's an entropic stabilization. Now, as you add a few percent of lanthanum and fluorine, then you start to get this pair effect. Your lanthanum ions and your vacancies over here tend to come next to each other because the vacancies are an effective negative charge, the lanthanums are positive charge in the lattice. Okay, if you have here's your sodium. If I put a lanthanum here with 3 plus and a vacancy here, then the vacancy and the lanthanum tend to try to get next to each other because the lanthanum, this has an effective positive charge relative to the neutral lattice, this has an effective negative charge relative to the neutral lattice, so they tend to form pairs, and then you're back to one new particle. You're not forming 3 particles, you're forming 1. But in very dilute solutions, the entropy always wins, and in a very dilute solution, the vacancies and the 3 plus ions go their separate ways, and they add three times as much entropy as you get in the liquid. So you very often get this entropic stabilization up here. We talked about this for some time, about 12 years ago, and an Australian who was here at the time as a research associate Mike Wadsley, who was here. We talked about this, and Mike Wadsley said, that's what the hell's happening, it's entropic stabilization because of this. And so we thought this was wonderful, and we started to write a paper on it, and then a paper came, while we were writing the paper, a paper came out by Dong, who worked in Stockholm, who proposed the same thing, so we missed it by a few months. And she got the whole thing right, needless to it. But that's what so this is really evidence, really strong evidence, I think, for this. And this, it doesn't have to be lanthanum fluoride, this can be calcium fluoride. If it's calcium fluoride, you don't get a maximum, but you get a liquid that is much flatter around this area than you expect it to. If it wasn't entropically stabilized, it would come down. Okay, so in the liquid phase, you tend not to have vacancies. The cations mix randomly with each other regardless of their charge, the same with the anions. Whereas in the solid, you have to take into account the possible formation of vacancies. Or there's other ways of the solid. The solid can do it by going in as an interstitial, for example. But the solid has more problems because it has a rigid lattice. It can't just locally adjust the structure around it. It has to do something, form a vacancy or form interstitials or something to fit itself into a fixed lattice. Okay, so that's the Temkin model. How do we then treat the Temkin model in a completely concentrated liquid solution? If we're going all the way, say we're going to take a system going from sodium chloride to magnesium fluoride and magnesium chloride and sodium fluoride, how do we treat the whole thing? Tune in tomorrow and talk about how we do that, a modification of the sublattice model for molten salt, for salt liquids. Okay, I guess, okay, so tomorrow at 9:30 instead of next week, next Tuesday. All right, we shall see you tomorrow. 1, 2, 3, go.